Good afternoon, guys. Today we're going to be talking about the quotient rule. The quotient rule is kind of like the product rule in a sense because they're both used for taking derivatives, and it's probably the one that people will be learning right after they learn product rule. So I actually made a video on product rule. I accidentally deleted it. So as soon as I finish making this recording, I will actually go and re-upload that. So that's my bad. I kind of oofed on that one. But after I finish this, I'll go back up and I'll upload that one. And also, I will have attached the notes, the practice questions, and the solutions. I'll have it pinned in the comments, probably as a link, as a PDF more than likely. So there's that. So we're going to start with the quotient rule. Disclaimer, if you have issues with people writing straight, please do not get angry at me writing crooked. I will try my hardest, but no promises. So, going on to the actual quotient rule itself, I'm going to show the notation for it. In the notes that I'll have pinned in the comments, I'll have it written out in words for you, but it's just to save a little bit of time. So, for any given function q of x, it doesn't matter what variable. I'm using q of x because we're talking about the quotient rule. You have a function in the numerator, and you have a function in the denominator. So, to define some variables first before I do anything, n of x is the numerator function. And I will call big D of x the denominator function. And I will call q of x the function that we're going to use quotient rule on. Basically, q of x is just the function that we're going to use quotient rule to find the actual derivative of it. So, all we have to do to actually find the derivative is you take the derivative of the numerator. Well, let me finish this. This is why I don't write in words. It takes a long time. So the derivative of q is equal to the derivative of the denominator, the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the denominator squared. So I'm going to erase off this half so I can rewrite it a little bit neater for you guys. I'm going to keep this top part. Derivative of the numerator times the denominator minus the derivative of the denominator times the numerator all over the denominator squared. There's a couple of different ways you could write it, but this is one of the ways. It's the way I'm going to stick with. So that's the quotient rule. So with that, we're actually going to go and identify different forms of the quotient rule. So if you have something like x plus 4 over 5x plus x squared, on this problem, when you're finding the derivative, you can use the quotient rule. If you have something like x to the third over x to the seventh, these are two separate functions. You can use the quotient rule, but it'd be easier to just divide it off and just say it's 1 over x to the fifth, x to the fourth. And then you use the reciprocal rule, which I'll go over in a different video. If you don't know reciprocal rule, you can just write it as x to the negative 4 and just use the power rule. And then we can have something like x plus 3 times x plus 5. This is a product rule. And finally, if we have something like x plus 4 squared, this is neither. This one is actually a chain rule. So if we're going to go through and identify these, this one is a quotient rule. This one, you can use quotient rule on it, or you can write it this way and you can use the power rule, or you can write it this way and use reciprocal rule. And then this one is product rule, and then this one is chain rule. So Q is for quotient, R is for reciprocal rule, P is for power rule, and C is for chain rule. So with that, we're going to go into some examples now. Quotient rule, I think, is a little bit more straightforward than product rule, in my personal opinion, but it can be a little bit longer. Doesn't necessarily mean it's harder. Once you get the hang of it, it's not too bad. So for our first question, we have y is equal to the natural log of x over e to the x. You can't simplify this down any, so we just have to go ahead and identify what's in the numerator and what's in the denominator. So we know that natural log of x is in the numerator, so we'll call this our numerator function, n of x. And we know that e of x is in our denominator, so we will call e of x our denominator function. That's denoted by d of x. So with that, we can go ahead and take the derivative. So we know that the derivative of y is equal to the derivative of the numerator, which is 1 over x, times the denominator, which is e to the x, minus the derivative of the denominator, which is e to the x, times the numerator, which is natural log of x, all over the denominator squared, which is e to the x squared. So we can rewrite this as the derivative of y is equal to e to the x over x minus e to the x times the natural log of x all over e to the 2x. Properties of exponentials: if you have something raised to an exponent raised to another exponent, you multiply the two exponents together. So after we do this, we can pull out an e to the x. So we can say that the derivative of y is equal to e to the x times, I'm going to use negative exponents. If you're not allowed to in class, you just keep it as 1 over x. X to the minus 1 minus natural log of x over e to the 2x. We know e to the 2x is equal to e to the x squared. So we can write off to the side, e to the 2x is the same thing as e to the x times e to the x. This is a property, they have similar bases, so you can just add the exponents. So we can actually say our final answer is the derivative of y is equal to x to the minus 1 power minus natural log of x all over e to the x. And that is our answer for the first question. I'm only going to be finding the first derivatives because it's a little bit simpler, a little bit more straightforward as well. If you want me to go and find second and third derivatives using quotient and product rule, you can let me know and I'll make that another video. So this is question 1. So for question 2, we have y is equal to e to the x over 7 to the x. True to form, let's identify our numerator and our denominator. So we know that e to the x is our numerator function, so we can say that this is n of x. And 7 to the x is in the denominator, so that is our denominator function. So we can say that's d to the x. So with that, we can just go ahead and apply the quotient rule to actually find the derivative of this function. So the quotient rule states the derivative of the numerator, which is e to the x, times the denominator, which is 7 to the x, minus the derivative of the denominator, which we know is 7x natural log of 7, times the numerator, which is e to the x, all over the denominator squared. So 7 to the x squared. If you're wondering what you do to prove that, basically, if you want to find the derivative of 7 to the x, you rewrite it as e to the power of 7 to the x. So you rewrite it as e to the power of natural log of 7 to the x. That's going to be equal to e to the x times the natural log of 7. And that is a chain rule. So right here, you would use chain rule. And if you use chain rule, you will get 7 to the x times the natural log of 7. When I do chain rule in the future, I'll actually make that one of my example questions. But back to this one. We know that the derivative of y is equal to, we can pull out an e to the x and a 7 to the x. So e to the x times 7 to the x. What we have left in parentheses is 1 minus natural log of 7. Also, just to note here, my 1's look like this, and my 7's look like that. So, in case you get confused by them. All this over 7 to the 2x. So just like before, we have 7 to the x in the numerator, and we have 7 to the 2x in the denominator. So that can actually give us just 7 to the x in the denominator. So our final answer will be equal to e to the x times 1 minus the natural log of 7 all over 7x. So this right here is our final answer. A little crooked, but that's our final answer. And you can just leave it like this. If you needed to find the derivative of this one, if you need to find the second derivative, what you would do is you would do a product rule on the top and you do quotient rule. So when you go to find it, it's still a quotient rule. So the derivative of the top is not just one function, it's 2. Actually, this is just a number. You don't need to do product rule. If there was an x, then you'd have to do product rule on that one. But I can always cover that in another video. I think one of my later examples will cover that, so I'll just talk about it then. But that's question 2. So for question 3, let's see. For question number 3, we have y is equal to cotangent of theta over secant of theta. Okay, so we can identify our numerator and our denominator. So cotangent of theta is our numerator function, n of x, and secant of theta is our denominator function, d of x. So what we want to do now is just use the quotient rule. So we can say that the derivative of y is equal to the derivative of the numerator, which is negative cosecant squared theta, times our denominator, which is secant theta. I'm going to put brackets around this because I'm running out of space, minus the derivative of the denominator. So the derivative of secant theta, we know that is secant theta tangent theta, times the numerator, which is cotangent theta. And we're going to end my brackets here. And this is all over secant theta squared. So a couple things stand out to me here. This tangent theta and this cotangent theta will become 1. So we can say that y prime is equal to, and secant theta and cosecant squared theta doesn't cancel off into anything. You could say, we can say No, that wouldn't work. So it's negative cosecant squared theta times secant theta minus secant theta, because this part becomes 1. Tangent is sine theta over cosine theta. Cotangent theta is cosine theta over sine theta. So it's reciprocal, so that's just 1. All this over secant squared theta. So let's go ahead and let's pull out a secant theta. So we can say y prime is equal to secant theta times negative cosecant squared theta minus 1. All of this over secant squared theta. So we can say our final answer is one of the secants will go away in the denominator. So we will have negative 1 cosecant squared theta plus 1 over secant theta. And that is our final answer for question 3. Trig functions are usually more in depth than the regular ones are. That's just usually how it is. So as long as you have your derivatives for them memorized, it's pretty straightforward. So that's question 3. So with that, we can move on to question 4. All right. So for question number 4, we have y is equal to tangent of theta over cosine theta. So we want to identify our numerator and denominator. So tangent of theta is our numerator, and cosine of theta is our denominator. So with that, we can go ahead and take the derivative. So we can say that y prime is equal to the derivative of the numerator, which is secant squared theta, times the denominator, which is cosine theta, minus the derivative of the denominator, which is minus sine theta, times the numerator, which is tangent theta, all over the denominator squared. So we'll just call that cosine squared theta. So secant squared times cosine is just secant. So we can say y prime is equal to secant theta plus, because we have negative 1 times the negative 1, sine theta times tangent theta, all over cosine squared theta. So you could do some big brain algebra here if you wanted to. Like you can pull out a cosine to try to get it to cancel off, because if you pull out a cosine from secant, you get secant squared. If you pull a cosine out of here, we can rewrite this as sine secant. We can rewrite it as sine squared theta secant. So we get 2 secant squareds. But for me, I'm just going to leave it here. I don't want to do any unnecessary algebra. If you really like algebra, you can. To be honest, I'm relatively indifferent towards it. But if you really want to do the algebra, you can. What you'd want to do is you'd want to plot a cosine theta. So this becomes secant squared, and this becomes secant. So it's sine squared theta secant, and then you cancel off one of the cosines, and that'd be your final answer. But I'm not going to do that. So that's question 4. So our next question is question number 5. So for question number 5, we have y is equal to 5x squared plus 11x cubed all over x squared. So if you want to, if you don't want to do quotient rule on this, say if you're taking this on a test, we can actually pull out an x squared. So off to the side here, we can say y is equal to x squared 5 plus 11x. And then we can say that's over x squared. So y is equal to 5 plus 11x, which means that using the power rule, y prime is equal to 11. So you can do that if you want to. If you want to test, that's probably the fastest way to go about doing it. Since I'm practicing quotient rule, I'm actually going to use the quotient rule on it and just show you that you get the same answer. So this is our numerator, and x squared is our denominator. So because we've identified 5x squared plus 11x cubed as our numerator and x squared as our denominator, we can just take the derivative. So I'm going to have to erase this. Just keep that 11 in your mind for when we get to the final answer. So this is one of the more lengthy ones. So we can say that the derivative of y is equal to the derivative of the numerator, which is 10x plus 33x squared times the denominator, which is x squared, minus the derivative of the denominator, which is 2x, times the numerator, which is 5x squared, plus 11x cubed, all over x squared. So there's a couple things that I'm noticing here. I can borrow an x from this entire expression here, so I can cancel off the x squareds, and then we can multiply the 2 out and see what we get. So let's do that. So let's take out some x squareds. So we'll have y prime is equal to x squared times 10x plus 33x squared minus, we can take another x out of here, so we can say minus 2x squared. That will leave us with 5x plus 11x squared inside. And then if you wanted to check that, if you distribute 1x back out, you'd have 2x here, and you'd have 5x squared plus 11x cubed. And all of this is over x squared. So let's go ahead and cancel that off. So we'd have y prime is equal to 10x plus 33x squared. This is the denominator squared, so this is x squared squared, which makes this not x squared but x to the 4th. Minus 2 times 5x plus 11x squared, all over x squared. So I'm going to erase the top. Well, let me just keep going with this. So if I write off to the side here, we know that this will be 10x plus 33x squared minus 10x minus 22x squared over x squared. Those 10x's cancel. This will become 11x squared over x squared, and that will be equal to 11. So, true to form, you do get 11 either way. One was a lot shorter. This one is a little bit longer, but you do get the same answer. Either one works. Matter of preference. And that is question number 5. So I only have one question left for you guys, and that's question number 6. So, there we go. For question number 6, we have y is equal to 7x plus x cubed over x squared minus 4x. So again, I can actually pull out an x here, and I can make it a little bit easier for quotient rule. So I'm going to go ahead and do that. So I'm going to say y is equal to x, 7 plus x squared over x minus 4. You can double check to make sure that works. If we distribute the x back out, we get 7x plus x cubed over x squared minus 4x if you distribute it back out. Those two x's cancel, so we can say that y is equal to 7 plus x squared over x minus 4. And this right here is what I will use the quotient rule on. So we know our numerator function is 7 plus x squared, and we know our denominator function is x minus 4. So with that, we can go ahead and find the first derivative. So the derivative of y with respect to x, same thing as y prime, is equal to the derivative of the numerator. So that's just 2x. Derivatives of a constant are always 0. 2x times the denominator, x minus 4, minus the derivative of the denominator. It's just, there's a 1 implied to be in front of there, so it's just 1, times the numerator, which is 7 plus x squared. All of this is over the denominator squared, which is x minus 4 squared. So you can't pull out an x minus 4, so what we can do here is we can say that y prime, the derivative of y with respect to x, is equal to 2x squared minus 8x minus 7 minus x squared over x minus 4. I just distributed out some stuff so then we can just simplify it off. This is one of those questions that doesn't take terribly long to simplify off. So the derivative of y with respect to x is x squared, because 2 minus 1 is 2, minus 8x, there's no other x variable terms, minus 7, all of this over x minus 4 squared. So that is our final answer. I suppose if you wanted to, you could try to factor it, but I do not believe that is factorable. If you have positive 7 and positive 1, that won't work. If you have negative 7 and negative 1, that won't work. For that to work, this would have to be a positive, not a negative. So that's our final answer. So those are the questions I have for you guys on the quotient rule. So if you want to take the derivative of this function again, you'd have to do another quotient rule, in case you're wondering. So that's all I have for you guys on quotient rule. I hope you guys learned something, and I hope you guys have a nice day. Thanks for watching.